plotted. It should be within the begin transaction and end transaction statement, right? So here we are going to perform debit and credit operation. We are going to perform multiple operations. However, it is treated as a single logical unit. If for some reasons the transaction fails due to software failure, hardware failure, network failure, power failure, right? Whatever is being done by an unsuccessful transaction should be undone, right? So you need to undo the effects of the failed transaction, right? So a transaction should occur completely or not at all. So that's the property of atomicity, right? Next, we'll study the property of consistency. So a transaction must preserve the database consistency, right? So if a transaction runs atomically in isolation, starting from a consistent database, the database must be consistent at the end of the transaction, right? So if your database is consistent at the beginning of the transaction, the database should remain consistent even at the end of the transaction. So consistency here means that money is not created or destroyed during the process of the transaction. The sum of accounts A and B before and after the end of the transaction should be the same, right? So for example, you transfer $50 from account A to account B. So the initial values of account A and B are going to be $1,000 and $2,000 respectively. So what happens at the end of the transaction? A value will be $950 and B value will be $2,050. However, if you find the sum of accounts A and B before and after the end of the transaction, right? So before the transaction, the sum of accounts A and B is going to be $3,000, 1,000 plus $2,000, which is going to be $3,000. At the end of the transaction, the sum of accounts A and B is going to be $950 plus $2,050, which is going to be $3,000. So money is not created or destroyed during the process of the transaction. The sum of the accounts A and B should be the same before and after the end of the transaction. If a particular database is consistent at the beginning of a transaction, it should remain consistent at the end of the transaction, right? So consistency requirements goes beyond the data integrity constraints, right? So you need to check for this primary key constraints, referential integrity constraints, foreign key constraints, check integrity constraints, and so on, right? So only if consistency is like you are going to check whether the department, I say that only the students of computer science and ECE, they can enroll for a particular elective course, then we can go for this check constraint, check department in computer science or ECE, right? Again, primary key constraints can be verified in checking the consistency requirements, and foreign key constraints also can be verified, right? So the next property is going to be isolation. So generally, whenever you want to increase the throughput of the execution of the transaction, right? So we allow multiple users to pay their tuition fees at a particular time. We allow multiple users to buy ticket for a cinema at a time, right? So generally, to improve the throughput of the system, we allow multiple access to a database, right? So the database system must take special actions to ensure that transactions operating concurrently should operate properly without interference from the other concurrently executing database statements. So the point is that at a particular point of time, more than one transaction may be executing on the same database, right? So for example, you consider there are two transactions, TI and TJ, they are executing concurrently on a particular database. For the transaction TI, it appears that transaction TJ has already completed execution, or TJ will start its execution only after TI completes its execution. It's known as isolation, right? So each and every transaction is unaware of the other active transactions that are present in a database system, right? So this property is referred to as isolation. And then the next property is durability, right? So once a transaction is successfully executed, right? So the money transfer has been done, its effect must persist in the database, right? So even if there is a system failure or a disk failure, it should not result in the database forgetting about the transaction that is successfully completed. So this property is called durability, right? So I book a ticket in IRCTC for online travel, right? So for a travel, I'm booking a ticket in online IRCTC website. So I got a confirmation ticket that I can travel from Trichy to Chennai, right? Once I book the ticket, there is a system failure, right? So the database crashes. So what should happen? So you should have some provision so as to recover the database system from the point of the failure, right? So generally what they do is that so the data will be written not only onto the database but onto a disk file, right? So generally we have some server and backup server. So even if one server fails, right, so we'll be writing both we'll writing the data onto both the server as well as onto the backup server. So even if one server fails, we'll be able to recover the data from the other server, right? So if you are going to store something in a desktop computer, so what you do is that you will be writing onto a database as well as onto the disk file. So even if the database crashes, you should be able to recover the data from the disk file, right? So hence a transactions action should persist across system crashes. So this property is called durability, right? So even if there is a system failure, we should be able to recover the system from the point of failure, right? So whatever we have studied, it's summarized in this single slide, right? So in transaction management, every transaction should support ACID properties: atomicity, consistency, isolation, and durability. So atomicity property, as you know that either all the operations of your transactions are reflected properly in the database or none are reflected, right? So it is all the operations or all the instructions in a transactions are carried out, or we need to undo the effect of the transaction. If it is a failure, it's known as atomicity. So consistency means execution of transaction and isolation. One transaction followed by other transaction, or one instruction followed by another instruction, preserves the consistency of the database, right? So isolation property, right? So even multiple transactions may execute concurrently. The system should guarantee that for each pair of transactions TI and TJ, it appears to TI that either TJ finished execution before TI started, right? So you have a pair of transactions TI and TJ. So it appears to TI that transaction TJ completed its execution before TI started, or TJ will start its execution only after TI is finished. So the idea is that each transaction is unaware of the other transactions executing concurrently in the system, right? So to improve the throughput of the database system, we allow multiple transactions to be executed concurrently. So however, each and every transaction is unaware of the other concurrently executing transactions in a system. So that's known as isolation, right? So for a pair of transactions TI and TJ, it appears to TI that TJ has already completed its execution, or TJ will start its execution only after TI completes. It's known as isolation. And the last property is like durability, right? So when a transaction completes successfully, the changes it has made to the database should persist even if there is a crash or a failure, right? So whenever I receive some acknowledgement, like I have booked a ticket and I got a confirmation from the system, right? So even if there is a system crash, so the database system should be able to recover the system from the point of failure. It's known as durability, right? So we'll study this asset properties, how it is being implemented, how transactions are executed concurrently, and so on in this unit. So this unit is about transaction management. So any transaction should satisfy this asset properties, right? So whenever you have a transaction, you need to know this two functions, read of X and write of X, right? So the instruction read of X is used to transfer the data item X from the database to a variable called X, right? So you are going to load the value from a database onto the variable X, which is present in a buffer in main memory belonging to the transaction that executed the read operation, right? So read of X means you are going to transfer the data item from X to a data item from the database to a variable called X. Whereas write of X operation, you are going to transfer the value of the variable X onto the main memory of the transaction that execute the write operation, right? So similar to your load and store command in hardware organization. So load is used to transfer data from memory onto the register, right? Here you are going to load the value of the variable from the database onto the variable X. It's called as read of X operation. And write of X operation is used to transfer the value of the variable onto the memory, main memory buffer, right? So we have discussed this transaction. So this is a simple example of transaction TI, transaction TI. So you are going to number transactions T1, T2, and so on. Here it's a generic name T suffix I, read of A is equal to A minus 50, write of A, then followed by read of B is equal to B plus 50, write of B, right? So read operation, you are going to load the value of the variable from the database onto the variable X, your variable A, right? So initially you are going to load the value of the variable or account A, you are going to perform debit operation, you are going to perform write operation, you are going to update the value of data item capital A